Hi, and nice to meet you. My name is Levente Szabados, and I'm coming from half Budapest, half Frankfurt. I teach at the Frankfurt School of Finance and Management, and I especially teach two types of things to two types of people. And it does work. Oh God, it even works. Super good. So I teach two types of things to two types of people. On the one hand, I teach deep learning to Masters of Data Science students, as maybe you are. Or data science professionals, begging your pardon. But on the other hand, what I found out is that there is an executive education, MBA education part of the school, and there is a big need for talking to those executive peoples who are super non-technical, non-coding, non-AI experts, because basically they will be our customers. Meaning that they will define some AI projects, and they will be the people who will order some products in machine learning. So whilst talking to these people and going back and forth between programmers and the business people, I just found out that there is a kind of trend which is not really visible in the media. Many of my friends asked, why are you talking about small data? Like, everyone is talking about big data, isn't it? That's the sexy thing. I mean, talk about the big one and don't talk about the small one. Who the heck cares? But I mean, my reasoning in this lecture will be that basically there is a decent scenario, and many more times we face this scenario that we theoretically should have enough data, but we just don't. Now the big question is practice, what we do when we don't have enough data. So as a motivation, and that was not me, that was a blogger guy, so he said that many times yours is not that big. So in the sense of your data is not that big, and even if you look at Google Trends, funnily enough, that the trend of using big data for everything went up for a while. But then it just trickled down in a sense, and there is kind of a cool down in big data. I heard executives complaining about they ordered the big Hadoop clusters into their companies. Now they have big Hadoop clusters in their companies and the same problems as before. Now what? So the big question is, how can we bridge the interesting things, not the hypey ones? That's what I want to talk about a bit. But let's just motivate ourselves with the problem of why is it problematic when we have small data, when we don't have enough data? Well, one of the causes is that it violates our core assumptions. Much of the machinery that has been built in data science was explicitly built with distributions in mind. You have a nice distribution of stuff. You can sample from a distribution. Okay, but if you look at this picture and you draw that 3 samples from the distribution, good luck with reconstructing the distribution from it, isn't that? It doesn't look like a distribution at all. It's a 3-point estimate somewhere, and heck can happen between them. So I would argue, and I will consistently come back to this topic during my talk, is that since our machinery is aiming these distributions, much of the fallacies, much of the problems that we inherit come from this thinking. First part. We generally have enough data, but we don't have enough data of one thing. Basically, class imbalance. Generally, we have patients in our database, but luckily enough, a very low percentage of them does have cancer. Even when I have hundreds of, or even 10,000s of x-rays of people, luckily, very few cancer cases. It turns out to be that if I'm trying to build up a cancer detector, I'm not really interested in that much in the general population. I'm explicitly interested in those small cases, the few cases that I want to model. So basically what happens here is that instead of this nice picture with the Gaussians, like balanced, 2 Gaussians, 2 distributions, these are the cancerous, these are the non-cancerous things, and there is a nice decision boundary that I can draw there. What happens in reality many times is that, I mean, if you look at the other part of the picture, the right part, is that the minority class, I mean the interesting class, the cancerous patients, are so few that generally the signal that comes from the big populace of other people's lung cancer x-rays is just really pushing away that decision boundary. And if you really explicitly look at it, you see two boundaries on the picture. One boundary with the normal line, the non-dashed, is the actual boundary that a simple classifier learns. But you visually see that it's not the thing that it should learn. Since the balance of the data is making it harder to at least learn something in general. So let's investigate a bit what we can do when we consider this very, very general case. Some of you may be bored because there will be some basic techniques in there, but some of the techniques will point us to quite recent papers and some interesting results. So 101, what to do? Well, obviously, from the business perspective, I'm not really interested, again, in the majority class or in the general populace. I'm more interested in the cancer class, in the thing that I want to detect. So why shouldn't I reflect this in my cost function? Why shouldn't I say that if you misclassify someone false positively as cancerous, I can anytime double check. But if you tell someone that he's healthy and he goes home, now that's a problem. So I would consider the cost, literally, the cost as a business. For me, cost as a hospital, cost as human society, and a cost function really, literally reflecting this, saying that, look, this is supervised learning, but we say that misclassifying the minority class should be way more expensive. We penalize you more if you do that direction of a mistake. And we don't really care that much if you do on the other way around. And what happens to be is that many times you can move this decision boundary. Again, you see the two lines, and now you have the labeling for that. The labeling says that without penalization, you get the solid line, and with penalization, or with cost-sensitive learning, so to say, you get the dashed line. So you can kind of engineer into your data science project something that's talking about the business value of what you're doing. Well, that presupposes that you already talked with the business people and they said, look, one is more interesting than the other. But that's just the beginning. What else can we do? Well, if we don't get any sense of this costs, we can try to do two things. We can do undersampling and oversampling. I mean, if I have 100 cancer cases and 2,000 non-cancer cases, I can try two avenues. One avenue is just I take those 100 cancer cases and I take another 100 non-cancer cases and make that the training data. That's what's called undersampling. I just undersample the majority class, which is very nice, quote unquote nice, because I made a decent big 2,100 data point big database into a 200 point big database. So I managed to lose a lot of my data. This is not a good way to do. So please don't undersample. What I can do, and what's arguably a much better idea, is doing the opposite. For each and every majority class, I repeatedly sample from the minority class, meaning that I just show the same patient again, and again. Which is at least meaning that the information that was contained in the majority class is not lost. So I rebalance the whole learning scenario, but without losing a bit of information. Again, this is super simplistic. Can we do better? Is there a better way approaching the whole thing? By the way, you see these links like sources links on the underneath, they are clickable. I hope that we will be able to share the presentation. I included the original publications or blog posts or something interesting on each and every page, so you can really dig into that technique if you want. So the big question is whether we can do any better. Yes, we can do better. What did we do when we used the repeated sampling? We generally use the same patient many times. What if we just generate some new kind of fake patients, like fake data points, synthetic data points in the sense. And the basic approach for this is just, what if we say that there is a region of points that behave the same? This is a reasonable assumption, since something like k-nearest neighbor, the simplest classifier, is exactly doing that. Meaning, if someone left to me is in class A, someone right to me is in class A, someone behind me is class A, I think I'm class A. You know, like you know your friends, type of thing. That is, that there is a topological assumption, so to say, that your data is not distributed totally randomly, that here is one class and there is another, but there is some kind of area or some kind of neighborhood that you want to try to model. If there is nothing, then good luck modeling, by the way. So, what if we say that we take some of the neighbors of an existing minority class data point and do a linear interpolation, meaning that, okay, if that guy over there is class A and that guy over there is class A, I physically say that, well, somewhere around between them I take a point, and there is a hypothetic guy that I just create, and say, okay, there should be another guy, and he should be like the average of the two others, and he should be also that class. So I just arbitrarily synthesize my data set, enrich my data set in the sense. That's the first approach. The second approach is basically just the same, but with adding some noise. I'm not just taking two guys and trying to draw a line and say that the average of them is also from that type, but add some noise to that. Push someone a bit further or bit in this direction. So, in the sense, and even I can do super sophisticated things, like the last point, this cluster-based approach, is that I detect the neighborhoods of similar people or similar data points in the space, and I just do this synthetic thing inside that neighborhood. So I'm not doing it just between 2 or 3 people or 2 or 3 data points, but I do it generally. Okay, this is meaning that something is going on with not just using the original data. So the revolutionary thinking that will lead us quite far in this path is that, what if we really manipulate our data? What if we create something from our data and use that? But we will get back to that later on. Or just vice versa. If we say that the whole approach that we took is having this topological assumption, meaning that there is a majority class is having a nice distribution, what if I just recast the problem at all? My problem was a classification. I said that please distinguish that 10 things from all the 100,000 things that are the majority class. What if I say that the majority class should be modeled as with some probabilistic model, saying that please tell me the probability that this point is part of the majority. And suddenly enough, I have an anomaly detection problem. I recast the problem. It's no longer a classification. I can assign a probability value to, well, this thing is looking quite probably as the same as the others. This thing is suspiciously different. I didn't have to draw a critical boundary. I didn't have to do a classical classifier. I just have a good model about how things behave in general, and what else is, or what is not behaving as general could be considered an outlier, and I cast outliers as something that are interesting. So I don't really detect whether someone has cancer. I can detect that someone is not looking like the other people. That's the thing. And maybe that's even enough. So I think it's sometimes this shift that happens. And from business perspective, it's the point where the data scientist goes away with the data and comes back later on and says, okay, you thought you want me to build a classifier. I didn't. Why? Why? Because I couldn't. There was not enough data. But what I could do is I can give you an anomaly detector and always alert you when something is strange or something is an outlier. And maybe that's totally good enough from the business perspective. But let's go into the serious business. Serious business is not that when we have few data points from one class. This is serious business when we have that much of data points. You know these psychological tests, I draw you 10 points and then you can draw a line between them. I always draw my mother, it's just always associating to that one. All the psychologists are laughing at me, that's the thing. So with those few points, you can do whatever. You can draw whatever. Or to recast it as a machine learning problem, if you have such few data points at all, I don't know how you can distinguish between a good model and a bad one. Let's formalize this. Everyone knows overfitting. Overfitting meaning that depending on the complexity of your model, you will approximate the set of data points better or worse. And it's visible that with a very simple model, you will say that, well, there is this kind of relationship between the data points, which is, we feel that it's not that complicated, it's not good enough. The middle model, it captures the nice arc on the data set. Humanly, we could judge, oh, well, it's looking quite nice. But still, there is some remaining error. It doesn't fit totally perfectly. The third model fits totally perfectly. Ideally, every point is on the line. Except if you look at the model, if you would zoom out or just shift a bit right or shift a bit left, most possibly left, then the continuation of this line goes up to heavens. Meaning that on this data, what we observed, it's looking super good. That's what you were joking with, or someone around sitting me, it looks super good on the data, except on the test data. So that's the case. That's typically the case. So having few data is inherently a problem because of the possibility of overfitting. And think about it. If you use a single hidden layer neural network, it's very good possible that you already have a too complicated model. So even if you have like 20-ish, 50-ish neurons in a single layer, that's being able to curve things quite nicely. So I think that's the big takeaway. What happened in the 80s and the 90s even hint on the big guru of deep learning admitted that yes, we understood new concepts of deep learning, but what really happened is that we started to try it on decent enough data sets. When we tried it on 100 images, it didn't work. When we tried it on 1,000 images, it didn't work. When we tried it on hundreds of thousands of images, it started to work. Well, this is one of the core things that's happening. But what if we can't? What if we have that few data? Let's jump in and try to solve that. Okay, there are the classics. Whenever there is overfitting, there are the classical, traditional statistical approaches. One, don't use a complicated model. Use a simple one. Use a linear regression. Always use linear regression, because that's good for your health. Except when you have a very complicated data set, then you use linear regression, and it's not that good for your health, isn't that? It just simply doesn't fit, which is not enough. Okay, regularize. You do dropout, you do regularization, L1, L2, you constrain the capacity of the model, you suffer hard, you understood the textbook, but I mean, that's not enough. You can switch over to other training regimes, meaning that you cross-validate, or you explicitly try to go into the thing which is called PU learning. PU learning is again, going back to that assumption that you only have positively labeled examples and everything else, which you don't really know whether it's positively or negatively labeled. So with some tricks in the objective function, you can try again with some tricks. But many times it happens that you have a complicated problem, so a simple model won't work, but you don't have enough data of that. It's getting worse, isn't it? What does it mean that we don't have enough data? This is a blog post that I've copied, and it's, I think, an ingenious blog post, Because the guy posed the question that what if I have two circles problem, so the inner circle is blue, the outer circle is red, with some noise. So the whole thing is generated like draw two circles, add some noise, draw some samples. How many samples do you need for, and I have to check because my memory is super bad, two inputs, 25 nodes in the hidden layer and one output. 25 nodes. It's a super small neural network, isn't it? How many data points do you need for this neural network to reliably learn these circles? I mean, learn to distinguish the inner circles from the outer circles. What you see over there on the box plots is that two things. One is the order of magnitude. Like you really step up your game. Since this is an artificial data set, the guy could generate more and more data points. It was not that complicated for him. The first takeaway is that, well, it's not in the hundreds. It's more like in the thousands for 25 nodes and up. But the other takeaway is the variance. Meaning that it's not just that the mean of the many training runs is higher, that this big box plot, the big variance just shrinks. Meaning that you will be in an like an overfitting scenario, in a not enough data scenario, your risk is bigger. Risk meaning that you observe something on the data set, even on the test set, but you're risking more in general. Because look at that variance that still remains. Okay, so how much is enough? For 25 nodes, it's in the thousands. God, what if we interpolated that to such a big model with millions of weights? God, why does this thing work? Isn't that? So, the big question, what Professor Moser is kind of an oldie in neural networks. He was famous in the 80s because he physically wired his house and tried to teach it to switch on the light on voice command. It kind of worked somehow, sometimes not. But so he's an oldie, and he put up this slide back in 2017 in Bilbao in his summer school. Why is this important? He said that generally the framework in which you should think about modeling is that there is one circle, which is all the possible models. It's a huge circle. All the possible weight combinations in a neural network. It's a gigantic set of models. What you can do is two things. Either you constrain the weights, constrain the model, meaning that you say, okay, choose only those networks with low weights, like regularization, or with sparse weights, again, regularization. You constrain the model class. On the other hand, it should still be compatible with your data. If I constrain the model and it doesn't do anything good on my data, then I didn't achieve anything, isn't it? So there is a set of models that works well with the data, and there is a set of models that works well under my constraint. If this is a well-constrained, if I constrain the problem well, in the sense, I can regularize the model and still get some results. If I do it badly, you see that small circle, that I will never get a good result, because there is no chance that the model learns anything. But the most interesting thing is what happens if you increase the amount of data. If you increase the amount of data, then the possibility of a model to just randomly fit your data is decreasing. If you add data, you regularize. If you add data, you make the problem more complicated, meaning that the possibility of the model to do arbitrarily random things and get away with it, quote unquote, is less. If you give more data, you risk less. Now that was the big assumption that the whole deep learning revolution was built on. Heck, give them way more data. How to do it? Well, My favorite kitties. Every presentation has to have kitties. There you have it. Internet is full of kitties, so that's it. We got over the kitties. But these kitties are not there for random. The original kitty is the leftmost one. What I can do is that I can augment, I can generate. For example, crop kitties, rotate kitties, do some transformations on them, since I know that a kitty from this angle and a kitty from this angle is the same animal, isn't that? So anytime I rotate the picture a bit, or anytime I just crop the half of it, I still expect that to be classified. I can use all the transformations that make sense in that domain. That was the general idea. Much of the, even in the 2012-ish to 14-ish papers that made big headlines, one of the underlying tricks was that they didn't really just train on the original data set. They did train on the original data set plus all the crops and skews and added noise and whatnot. So they enhanced or augmented the data set, so much so that even TensorFlow data sets has this built-in augmentation pipeline in there, what you can do. But what turned out to be more interesting is, in the sense, something pointing towards what is called semi-supervised learning. What if I do a classifier on, like, transforming the kitties, rotating them a bit right? I do a data set of rotating all the images, train a classifier. I do another rotation the other way, train a classifier. Take these two models, do an ensemble of them, I mean make them vote, basically. Like that's the basis democratic part of machine learning is the ensembles. So make them vote on unseen data, which is not labeled. Just basically label my own data, dog food myself. This is called semi-supervised learning in the sense because you have originally some supervised signal, but you gradually lose that supervised territory. So you just go into that terrain of I will label noisily something which I didn't see and feed a new model with the totality of the data. If you take this seriously, 2 years ago, approximately, or 1.5 years ago, some people took that so seriously, some people at Facebook, that they said that, look, we have ImageNet, which is, I think, in 10 million-ish images for 10,000 categories, like giraffe, dog, whatever, airplane, you name it. What if we do a competition? Take this data set and train a neural network, and take the same neural network and train it on something else. Something else is Instagram. Instagram is a super noisy data set, isn't that? If you look at people, what they put under in hashtags, there is all kind of rubbish in there, isn't that? You can expect total noisy, random joking, memes, Donald Trump, not Donald Trump, whatever you want that. But what if you take this huge data set, which is in the trillions of data points, consider it noisy, and train something on it? Turned out to be that the later model, trained on the super noisy but huge data set, performed better than a model trained on the clean data set, which was smaller. And everyone got a shock, in the sense. Anytime you post anything to Instagram, you know that you're helping Facebook building the models, meaning that you're tagging for them. That's one of the takeaways. Now, seriously. The takeaway is that a huge data set labeled noisily is maybe better. Thus, using this dog fooding approach of getting weak learners, weak models to label kind of noisily a data set and use that for a global learning approach is plausible. Please observe the links over there. There are many, many, many links, some of them super recently. It is a hot space. Hot meaning that meaning that even on Facebook scale, there is not enough data. So even Facebook is trying to go to bigger and bigger data sets, and some of these techniques will enable that. What was the underlying assumption that we had till now? The underlying assumption was that if I want to distinguish the top half moon from the bottom half moon, I ideally would use only those data points that are in the data set. One half moon top, one half moon in the bottom. But as said, it is a very, very poor estimation of a distribution of all possible blue points and all possible red points. And that's where the guys who produced this paper called Mix Up were kind of enthusiastic about. They said, what if we really get rid of that assumption that we have this point somewhere in the space? What if we really want to do some distribution, learn some real distributions? What if we do it like we take a blue point, take a red point, kind of average them, take some lambda times a blue point and lambda times a red point. One minus lambda times, sorry. So to kind of a weighted sum of them, basically. And what if we take a weighted sum of the labels? I say that this point is now looking 80% blue and whatever, 20% red. Turned out to be that because of the thing, which is a super simple thing that you can do before training, you generate new data points with a new type of label being no longer a distinct label for being blue or being red, but this kind of probabilistic label of half blue, half red type of thing. With one-hot encoding, it's very elegant. You can do it like numerically, very elegantly. Turned out to be that this is giving a huge boost to models. Huge boost in the sense that you're no longer constrained to say point, 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 this is truth, this is the other truth, and we don't know what's in between. We don't know about generally that space that all this whole thing is happening in, just observing here and observing there. This is kind of a blasphemy in the sense of they moved away, that's why they say that they move away from empirical risk minimization. They move away from observing, and they are trying to move into interpolating or extrapolating, if you want, which is, I think, a very interesting task. That also says that maybe the data points that are in our data set are not created equal. Maybe they are not equally meaningful. Maybe there are some more interesting and less interesting data points that we should use. Who tells us that we learn the same amount from any of them? This is kind of a recent paper, I think less than a couple of months old, I think, is dataset distillation. Dataset distillation is very, very annoying. Annoying in the sense that someone took MNIST. Who knows what MNIST is? Hands up. 1, 2, 3, 4, 5, not enough. MNIST is 60,000 handwritten digits. It's kind of the introduction to using more sophisticated neural networks. Like someone labeled it was the US Postal Office, and someone writing the zip codes, they labeled it that this is a 0, this is a 1, this is a 9, whatever. 60,000 of these 10 categories, 0 to 9, and 60,000 examples. Now what these guys did is they initialized the network and let it learn to classify 0, 1, 2, 3, 4, 5, whatever, 9. After getting these networks to reach the final point, they had super good performance. This is a solved problem, 99.99, whatever accuracy is achievable. Everyone is having this hype of doing 0.01% more. So they got this network, which was basically perfectly learned, And what they did is they said, can we synthesize 10 images, not 60,000, 10 images that are representing the prototypical 0, the prototypical 1, the prototypical and so on and so on. Can we do gradient descent in the other way around, meaning that can we modify the pixels iteratively to come up with these prototypes? And after we came up with these 10 prototypes, can we train a neural network starting from the same initial values that the network we had, only on these 10 examples? And it turned out to be that you can. Meaning that there are some super meaningful data points. They haven't been in the original data set, they are synthetic, but most probably they capture some essential parts of the distribution, the data distribution, and capturing much of the information. So maybe you don't need 60,000 examples to learn classification of handwritten digits. Very interesting, I think. But let's move on. So, what can also be done if you, as a poor data scientist, don't have enough data? Well, you can do transfer learning. Transfer learning meaning that someone else, someone at Google, someone at Facebook, someone at Uber, someone at these big OpenAI, someone had the time, the TPU capacity, the GPU capacity, the money, the whatever, the data to train a big model. You take that big model that was trained on something else and try to apply it to your problem. Much of the medical imaging startups do this. The medical imaging numbers, like how many real X-rays of real patients you can get, is very limited, so that you're kind of forced to use a classifier that was trained on not X-rays, but giraffes and whatnot, another problem, and try to get that to transfer learn to your problem. Everyone has to do transfer learning. This is kind of now the state of the art. Many times in natural language processing, where I come from, it's kind of a mandatory thing because no company has gazillions or trillions of words of text, only a couple of hundreds of thousands. So this is one thing you can do. But what is really interesting in this is that you can use something which is more state-of-the-art, so to say. Who saw these Van Gogh painting things? A model where you can input a picture and Van Goghifies it, Van Goghifier, or face generator, these same things. These are called generative adversarial networks, or in certain cases, conditional variational autoencoders, which is not that interesting. They are models that they are learning the distribution of all possible Van Gogh paintings in the sense, and applying that Van Gogh style on everything what's fed in there. Now these models are now basically toy models out there. I don't think that the world's GDP will explode if everyone can be able to Van Goghify his pictures. Maybe Instagram will have a nice day, but no one cares. Except that the distribution that you can learn in an unsupervised manner, like the model you can use to your supervised task. So if you have a good face generator that generates nice faces for NVIDIA, someone from NVIDIA, nice face generator, I would argue that that model, if you take that model out and apply it to your problem, is a very good face discriminator. Can be built on top of it. So I think watch that space, that will come very soon. It had some hiccups, but now people are trying to iron those hiccups out. So maybe there will be an interesting new wave of transfer learning going on. And yes, you know the joke. Can I get out of that penalty list? Yeah, why not? So if you don't have enough data, why don't you ask for it? Sounds trivial, but why don't you go to a user and ask for it? Or more specifically, why don't you design your system so that poor user, just doing his own job, is labeling data for you? I think What do? We are, anytime we post anything on Facebook and like it, we are helping to label the world's biggest recommendation engine. Do we know and do we care? No. I just want that kitty. That's it. Why not? So how could you design in a business scenario something which actively participates in the user's workflow and labels the data for you, and you're just out of the waters? You no longer have the problem. Even if you are a bit more wise and use something which is called active learning, meaning that I don't want you again to label everything. Label the interesting stuff. And as I've argued, there are points in the data distribution which are more informative than the others. There are these prototypes, there are these spaces that are worth labeling. If we can design algorithms, and that's what basically what active learning is doing, to pose the right questions, then maybe from an order of magnitude less questions, I can build up a better database. Basically, that's what's worth experimenting with. And there is another very recent approach, is that use comparisons. So no longer try to do discriminative models, but try to do comparison models. Some people argue that for a human being also it's very difficult to say your age. But it's kind of simple to say that you are younger than me. Comparison is less complicated. So maybe some of the models that are coming up, came out recently, will solve this part. What is the takeaway here? The takeaway once is that you have to understand the risk you're running in a real life scenario. Jay, my model is 90% accurate. Means that 10 people are dead, isn't that? The 10 others from the 100. It's not the same when you say I am just tagging marketing images than tagging people's lives. So I had the fortune to comment on the European Union's Trustworthy AI initiative. There is a position paper, and this notion is very crucial, that in proportion to the impact on people's lives, you should consider your risk. And if you say that you don't have enough data for that level of risk, then you just don't go there, or use these techniques, or do whatever. This is one takeaway. The other takeaway from active learning from me is that you shouldn't replace. If you say that I will do the world's best classifier, I will deploy it out, and I will fire everyone in that department. Good luck. The classifier will for sure fail. If it's 99% accurate, that means it's 1% inaccurate. In 1% of the cases it will fail, people find that failure, and you won't deploy that model. But if you do a suggestion to the colleagues, and those colleagues are saying basically yes to the suggestion 99% of the time, the colleagues are happy, you didn't fire anyone, productivity goes up, and no one's feeling is hurt. So don't try to replace people, try to augment their workflows, because they can give you feedback, teach your model, and you both can get far. That's, I think, one of the points that we should really emphasize while communicating between technology and business. And finally, two thoughts as an epilogue. These are very recent papers. Even I don't really understand the full depth of them. Like, I just read them and what the heck? Is two things. Inside the dataset, as I argued, there are these crucial so-called, forgettable examples. Why they are forgettable? Why you do this iterative learning inside the convergence of a neural network? Sometimes you modify the weights a bit, and they fail on an example that they didn't fail a previous time. You know, practice, fail, practice, fail. But the interesting is that there are examples which basically, after the first 2 rounds of training, are stably classified all over the place. Meaning that they are not interesting. Meaning that they are never misclassified, meaning that why are they there? This paper tried to really literally forget or delete those examples which are not contributing to the learning, which are not that interesting to be there. And in this MNIST dataset I've mentioned, from the 60,000 examples, over 90% could be deleted without losing accuracy. Meaning that it's way better to have some interesting examples. Good luck defining what interesting is, but we are working on it. So it's way better to have the good examples than the many. Maybe after big data, the small but precise data will prevail. And finally, do we need that big of a model? The thing is that this paper, I think 3 weeks old, tried the following. What if we initialize a network randomly and let it train for a little bit and observe that certain parts of the network are trying to increase their weights, increase their presence, increase their confidence, contribution to the final solution. And what if we only keep those? Meaning that we do a big network, random initialization, let it learn a bit, see who is the interesting learner in that, and throw away everyone else. Amazing pruning happened, meaning that they could reduce the size of the network with orders of magnitude. So maybe it's not just that we will go into a small data, but also maybe a small network or a small learning scenario. Maybe after deep learning, something interesting as a smart learning will happen. We will see. Even I don't know. Please keep up. Thank you.